3D tension stuff. I don't know.
Okay. All right. I don't have much in the way of announcements. I usually try and check to see what the status was on the homework, but I've had meetings all morning, so I did not have time to like sit down and check. I mean, I just wrote this announcement slide right before class. Okay. I do know that 9.1 was due today. Hopefully the derivation went very well. What was this? WL squared over 8. Good, because we're going to use that today. That was the maximum moment due to a uniformly distributed load put on a simply supported beam. An aid that I had you derive was the most ubiquitous aid, period, in structural analysis. Because the most common beam that we analyze and design is one that's simply supported, and all beams, at a minimum, must be able to withstand their own self-weight, which is modeled as a uniformly distributed load. So that model is the most common one that we use in engineering, period, which is why I wanted you all to do that one by hand. Okay, like I said, though, this week, the focus is the real world, and we are going to continue our discussion with the real world by looking at tributary area. Okay? Now, I'll say a couple things about this. We've already done tributary area a bit with the truss, but I sort of walked you through the tributary area aspect on the truss, and I kind of want to be a little more general about this. Let me grab my little notebook here. I kind of want to be a little more general about this today because I want to apply tributary area in a little bit more of a real scenario and show you how we would use this for an analysis problem for a more complex structure. Okay, so the idea is this, okay? All right. So let's just take this problem. One that you all have, been able, to do. Let's just put it like this. If you can't analyze this problem, like if I gave you some numbers to go with it, if you can't analyze that, then I have just failed as an instructor, okay? Everybody in here should be able to compute reactions for a beam like that, draw a shear diagram, draw a moment diagram. I'm assuming that's not a problem, right? Okay, but here's the thing we haven't really discussed, which is why I wanted to sort of close the class on this, is how do we take a building, a real building, and turn it into that? Right? That's kind of the problem, right? I mean, we haven't really talked about how to apply these in a real scenario. And what we need to know now is how do we take loads, real loads on structures, and distribute them to a structural system, okay? So we want to be able to turn a building into that, okay? First off, I do want to talk about the loads themselves. One of the things that has been a little bit of a mystery for a lot of the semester is I give you a problem and I give you some loads. Where do those loads come from? Okay, the load on that beam is 2 kips per foot. I mean, did you just miracle that into existence? Where did the 2 kips per foot come from? Well, structural loads are, a function really of 3 things, I would say. What the structure is made of, what the structure is being used for, and where it is, okay? So what it's being made of, what I mean by that is all structures need to be able to withstand their own self-weight, okay? So as an example, if you have a building that's made out of steel, structural steel weighs 490 pounds per cubic foot. So we can take that 490 pounds per cubic foot and determine weights of the structure pretty easily as, unit weights times volumes. Reinforced concrete weighs about 150 when you account for the rebar, and what have you. The other thing that we can do as engineers is we can either calculate dead loads based on unit weights, or we can also look up loads dependent upon the type of elements that we're dealing with. So for example, these are some common floor dead loads, and dead loads and live loads are usually expressed in a pounds per square foot basis, because what you'll do is you'll take that pounds per square foot and then apply it to beams, columns, trusses, and what have you. So let's take a look at floor dead loads. So framing, that would be sort of the building itself, the beams and the columns and what have you. fireproofing the metal deck. So if you've ever been in a commercial office building, or maybe if you go into the stairwell, you can actually see sort of the metal pan that serves as the formwork for the reinforced concrete, you know what I'm talking about? So we've got metal deck, concrete, whether it's lightweight, normal weight, what have you, floor finishes. So is the floor, does it have tile on it? Is it slate? Does it have a hardwood finish on it? And so dependent upon those floor finishes, those are different weights that we would have to account for, right? So like for this building, we would have concrete and then we would have carpet, you know what I mean? Like the carpet isn't, feathers, like it does have some weight to it. It wouldn't be, 15 pounds per square foot, but it's gonna have some weight that you would account for. Make sense? All right, now that's dead loads. What about live loads? Okay, so I gave you when we were doing influence lines, I gave you a definition about dead versus live that was analytical. And so what I meant was dead loads are permanent and live loads are transient. Live loads have the potential to move, right? And that's still true, okay? But we're starting to dip our toes with this lecture a little bit into structural design, like what you would talk about in steel design or what you would talk about in concrete design. And live loads, from that perspective, the word I like to use is occupancy. A live load is prescribed based on what the structure is being used for. Okay? So as an example, if we're talking about a school facility like this one, we're going to have different uniform loads that we would consider for the classrooms, different loads that we would consider for the hallways. So I'm curious, let's just ask you, why are the hallways, why do they have a higher PSF load than the classrooms? Why would the hallways have more, why would we have to design them for a heavier load? More people, but when is that really a problem? Not just when class is let out, but also during emergencies, right? If there's a big fire, there's gonna be a lot of people in the hallway, right? In fact, so like one of the things I talk about in a steel design class or a concrete design class is some of the philosophy that changes dependent upon how you design, let's say, commercial spec office space versus how you design a hotel. Like when you design a hotel, when you're designing the structure for a hotel is very delineated in terms of where the rooms are and where the halls are. Like it's pretty fixed. It's not really changing. Nobody comes in and reconfigures the arrangement of a hotel very often, okay? But has anybody ever been in just a big office building before? I imagine many of you are. Well, whenever you're a developer and you're developing a commercial office building, you as the developer want to be able to sell off or rent off certain space in that building. And usually you want to do it on like a per square foot basis. So maybe an accountant comes in and they says, I want this much of the space. Okay, well that's this many square foot, rent is X times square foot, so this is how much the rent's going to be per month. Make sense? Well, if you're a structural engineer and you're working with the developer doesn't want to have their hands tied. Well, that has to be a hallway and that has to be a room. So usually when you're designing commercial spec office space, you design everything as if it's one big hallway, right? So you would use like 80 or something everywhere, okay? Now I am actually skipping some details because there's things like live load reduction and what have you, which I'm not really getting into. But I just want to say that's kind of the idea. Now these loads can also change dependent upon the type of structure you're dealing with. So like for example, if we're looking at offices, so we might have 50 pounds per square foot and what have you for an office, but I don't have it on here, but if I had libraries you have to design for like 150 pounds per square foot. Why do we have to design libraries for 150? Because there's all those books that students don't read, right? So, it was a joke, not very funny. But in all seriousness, like the books are a stationary load, and I could really get into the design aspect of it and talk about live load reduction and how you don't reduce library loads. It could get really involved if I don't hold myself back because I actually want to get into this. But it's a lot of really cool stuff. On a side note, the floor system in Drinko is actually really interesting. They use a waffle slab, so it's a two-way reinforced concrete slab. So it's a slab and there's ribs that go this way and ribs that go this way, and if you look, it kind of looks like a waffle. So because it's got to hold up a lot of weight. So I don't know, just kind of cool. Okay, so I just wanted to have a little bit of discussion about loads and where they come from. The one load that I didn't mention actually is environmental loads. I said where they are. So we have to design buildings also to withstand wind and snow, and those are largely a function of where they are. So like for example, it's not terribly difficult to go to a given map and find, based on we're at Huntington, West Virginia, determine what is the ground snow load. You know, around here it's going to be about 20 pounds per square foot. And then we have a few calculations where we have to take that and convert it to how much load we expect on the roof, and then we treat it, you know, largely the same as we do everything else here. With all these load aspects that I'm talking about, there's a lot of details that I'm skipping right now, and we'll probably talk about that more next semester in concrete design or steel design. Well, I'm teaching steel design. So. Now, let's say we've got these loads, what do we do with them? That's where tributary area comes in. So the definition of tributary area is how much a member, the area on a given floor space that a given member is responsible for. And it's best defined as the area that's bounded by lines located halfway between adjacent elements. Okay? So for example, I've got a column, if you look behind me, I've got a column right here that is supporting the external facade on this side of the building. And I also got a column right here. So I'm imagining, I don't have the floor plans with me, but let's say we got a beam right here from this going this way, and we also have a beam right there. So let's just look at this beam right here. So the tributary area for this beam is going to be all of this halfway over to this one. And then once we get over here, that one's going to be responsible, right? So this beam is responsible for all the floor that's halfway over to this beam and then halfway over to this beam, okay? Now, I'm doing some assumptions of one-way behavior, and I'll talk about that here in a little bit later, but for the most part, that's a pretty safe assumption. And what we can do is we can use this concept to perform what's called a load takedown on the structure. And basically what a load takedown is to take all the beams, the girders, the columns, and all that, and determine how much load goes on each element. And with those loads, we can begin design, okay? Now, let me kind of give you an idea of how the concept of tributary area would work. So let's just consider a generic floor plan, okay? So I just want to make sure we all kind of understand what we're looking at here. So first off, has anybody ever seen like blueprints or plans of a floor plan in a building? Anybody ever seen that before? If you haven't, usually what you'll see if you're looking at it in plan view, so remember plan view is being in the helicopter and looking it down, you will see a series of, usually it's like letters on one side and numbers on the other, okay? So that each of these intersection points, like we can talk about column B2, column C1, and what have you. And to be clear, those are columns. At each of these points, there's a column because in plan view, the columns are coming out of the ground. So all you would see is just, you know, like a square or an eye shape or what have you. So we have a column, not necessarily at every grid point, that's up to the architect and the structural engineer working together, but for this building it's pretty simple. And then between these we have a series of beams and girders, okay? Now I will just be straight, that there are, in the real world, we have beams, we have joists, we have girders, we have stringers. Those terms are used fairly interchangeably, okay? And there's no real hard and fast rule over what refers to what, but what I like to do to keep things straightforward is I like to say that the beams frame into the girders, okay? So this girder right here, or this girder right here, is going to be a fairly large element, and there's going to be a few smaller beams that frame into it, okay? Does that make sense? All right, I'll show you a pretty familiar example here in a bit. Okay, now whenever we're doing a load takedown, what we'll typically do is we'll start off with the smallest element and then sort of work our way out, sort of a hip bone connected to the leg bone approach until you get all the way down to the ground. So if we start out with one of these beams, okay, we say halfway over, and we can collapse that, and I'll show you what that means here in a second, into a distributed load on that beam. Now this problem, again, is something I hope that everybody in here can analyze, right? So let's say we've got this beam. Remind me, what are the reactions for this beam? what you all derived that? What was it?
Weight times L over 2.
What is it? Yeah. WL over 2. Okay? Now, I want to ask you a question for these beams. Okay? So these beams. So there's a reaction here. So beam, if we're looking at this beam's right here. So there's a reaction here and there's a reaction here. Where do those reactions go? Like, do they just, I mean, like, where do they go? The beams are connected to the girders, right? So there's a girder here, right here, and I've got beams here, beams here, beams here, beams here. So a way of idealizing it is the girder could be seeing a series of point loads. And what are these point loads? They come from the reactions from the beams connected into it, right? And then these girders are going to have reactions. And where are they going to go? Well, to the columns, right? So see how you can go hip bone connected to the leg bone all the way to the ground? That's kind of the idea. Here's a more real-world example. Anybody familiar with this picture? This is the 3rd Avenue parking garage right down here, right? So the 3rd Avenue parking garage doesn't actually use beams and slabs separately per se. They are using a precast concrete element, and the precast concrete element is what's called a double T. Okay, so a double T cross section kind of looks like this. So it's precast. Oh, what's going on? What's going on? Did I lose my recording? I'm going to do this. Okay. All right. So the elements in the parking garage are pre-top double T's or precast double T's. They kind of look like this. And the way that it works is you actually precast those at a precast plant, and then these units are shipped to the site on a truck, and then they lift these in place. So they're not separate beams per se. They're all integrally cast. Excuse me. But for the purposes of our tributary area discussion, we can treat it like that. And what happens is, if you look at these beams are a lot smaller from a cross-sectional perspective than the associated girders they're framing into. Okay, these girders are a lot beefier and a lot deeper. And the reason why is because their tributary area and the load that they are responsible for is far larger than the beams. Okay, and you're going to see that pretty directly here in a second. Any questions? All right. I think the best way of evaluating this is, let's just do an example. Okay, so I have a floor system, and I'm going to pull the floor system up here on the next slide. And I am subjecting that floor system to a 20 pounds per square foot load. Now, before we get into this, okay, I just want to capture the fact that we are only talking about 20 pounds per square foot. We are not talking about a lot of load. And I want to determine, so what we're going to do is we're going to sketch the tributary area on a few key elements, and then we're going to determine a few things. We're going to determine the distributed load on a typical interior beam. We're going to determine some concentrated loads on a given girder, and I just picked one, just C2D2, I just picked one. And then we're going to determine the axial loads on a column. And I say that 20 pounds per square foot load, I just want you to keep that in your head, because 20 pounds per square foot is not very much. It's really not. I mean, we're talking about a box about that big and 20 pounds on it, okay? But everywhere on the floor system. And I'm easily going to turn that into 120 kips by the end of this example, okay? So these loads, they add up, and they add up quick, okay? Now, the floor system that we're going to look at is this floor system right here. I'm going to pull it up on the notebook right over here. So I'm keeping it basic for the purposes of our discussion. So we have here a really straightforward floor system, okay? So one term I did not mention is the term bay, B-A-Y. I would say that this floor system has 9 bays, okay? Because there's 1, 2, 3 bays, 1, 2, 3 bays. Like bays are the sort of square regions or the regions between columns. So think of it like a checkerboard, okay? Like a common bay spacing in steel buildings is usually like 30 feet by 30 feet. That's pretty common. Not always the case, but that's a non-unreasonable bay spacing. Okay? Sound good? Okay. So what we're going to do is we're going to handle this from a tributary area perspective. And the first thing I want to look at is I want to look at the floor beams. Okay? So let's consider those. My pen doesn't like me this morning. Beams. Okay, so what we're going to do is we're going to pick an arbitrary floor beam. I don't know, let's just pick that one. Let's pick that one right here. And I want to draw the tributary area for that floor beam. Okay, so here's the floor beam. So how long is the floor beam? Let's make sure we're paying attention. 30 feet. So it's a 30-foot long beam. And I'm going to draw the tributary area. And I propose the tributary area is halfway to the next beam, halfway to this beam. Okay? So the tributary area for this element is like that. Okay? So, just so we're on the same page, what is that width right there? 10 foot, because it's 5 on each end, right? So I'm going to call this WT. The tributary width is 10 feet. I'm calling it the width, okay? All right, so for this floor beam, we have a tributary width of 10 feet and a length of 30 feet, okay? Now, please do not make fun of the artwork that I'm about to do, but I'm going to do my best because I want to make sure that you all are seeing this three-dimensionally. Okay, so what's going on is I've got a slab that looks something like this, okay, and I've got a series of I-beams that are doing this whole thing. All right, and we'll try and give this some relief. We'll try and actually finish this thing out. All right. Okay, we'll finish that part out later. Okay. So here's the floor beams, okay? And what we're saying is that this dimension here, this is the length. And then this dimension right here is the tributary width, okay? And what I propose, here's what I propose. I propose that if we're talking about this beam here in the middle, okay, that this beam is responsible for all of this. That's what that beam is responsible for. All of the tributary load, all of the load that falls on the tributary area, because anything on the left or the right is going to be picked up by the beams on the side. Make sense? Okay. Now, here's what I'm going to do, okay? What I want to do is I want to take this model and I want to turn it into this, okay? I want to do this. How did I do on my 3D art skills? Thank you. You could just say, you know, it sucks, Dr. Mike. Just, you know, we're just trying to make you feel better. It's horrible. No, okay. So what I want to do is I want to take this problem and I sort of want to remove the three-dimensionality of it. And all I want to deal with is this. I want to turn that into this. Okay? I want to turn this into this. Why? Because this is just that. Okay? And I want to take this building and turn it into a problem that me as a structural engineer just loves to solve. Okay? So I'm curious, how do we calculate this? Okay? If this pressure load up here is 20 PSF, my question to you all is, what's that? How do we compute? So if this is 20 PSF, how do we take 20 PSF and what do we do here? How do we turn this 20 PSF to that? Is this 20? That's what you do. Okay, so let's investigate both situations. Okay, so what is the tributary area? I'm asking, what is the tributary area?
300 feet.
300 square feet. Yeah, so the tributary area is 300 square feet. So if I take 20 pounds per square foot and multiply it by the tributary area, I'm going to get 6,000 what? Pounds, right? But this needs to be a pounds per foot, right? So I'm going to take that pounds per foot. What am I going to do with that pounds per foot? I'm going to take that pounds per foot and divide it by 30, right? But if I take 20 times that divided by 30, why don't I just take 20 times that? Make sense? So I propose that W is the pressure times the length, or the tributary width, sorry. Exactly. So 20 pounds per square foot times that's 200 pounds per foot. So I propose that we are now dealing with this problem. Okay. Now, I don't know about you, but that should be a problem that's easy to solve. So notice how what we've done is we took a three-dimensional structure and we broke it down into something that we can solve very easily. Okay? Now, I do want to ask a couple questions about this. So, first thing I want to ask is, what is the reaction? Okay? And I'm going to call this reaction RB for the reaction for the beam. And you're going to see why here in a second. And as we identified just over there, that's WL over 2. So 200 over 2 is 100 times 30 is 3,000. 3,000 what? Pounds, right? Or 3 kips. Okay. Hold on. Sorry, give me 1 second. I'm going to move this down because I didn't want to have to copy this over and over again. So I made that a little easier. Okay. So here's our beam reaction. Okay. What about M max? Okay, so I'm just going to go ahead and compute M max. And so what do we get for that? What's that? Did you square it? You did? Hold on. I got 22,500.
Yeah, that's what I did.
Did you did instead of 8?
No, I put 1,200 instead of 2,000.
Ah, that'll do it, yeah. Okay, what are the units? 22,500 what?
Pounds.
No. It's a moment.
Foot-pounds.
Foot-pounds. Or 22.5 foot kips. So this is the maximum moment that this beam is responsible for. So then what I will do is I will select a beam that can withstand that load. Okay? Does that make sense? All right. So far, so good? All right. All right. So now let's look at the girder. And the girder that we chose was C2D2. Man, there's no R's in this grid. Shame. Star Wars, anybody? No jokes this morning, I guess. No laughs. Okay, so girder C2D2. So what are we talking about? We're talking about this girder right here. So what's the tributary area look like for this girder? And while we're not actually going to directly use that tributary area, I actually want to draw it because I want to make a point about it. Okay? What is it? Halfway up, halfway down? So the tributary area looks like this. That's the tributary area. It's bigger, right? So it is responsible for more load, okay? More load, all right? Now, I do want to make a couple points about this girder, okay? There are two ways of distributing the load. The first way is to just do what we just did, but do it bigger, right? So the beam, in this case, is 50 foot long, and the tributary width is 30 feet. So just do everything that we just did, but just do it for those inputs, okay? But I'm going to do it a little differently, okay? Instead, I'm going to do with this, I'm going to treat it differently by considering these reactions, okay? So notice right here this girder has beams framing into it, right? Every 10 feet, there's a beam framing into it, right? So what's going on is we've got, oh man, this is going to be tough to do. I'll do my best. So here's a girder. Okay, that's the best you're going to get out of me. Okay, that's the best you're going to get me. And then right here, like let's say at this point right here, we have a beam. Oh, that's bad. Framing into it, but then we also have another beam coming in back here, right? We've got another one here and another one here, okay? So I propose what we can do is we can model this as follows. We can model 4 point loads there, okay? Now, I'm going to call these point loads P. All right? Let me ask you a question. Let's go back to our previous problem. So our previous problem, we had RB was 3 kips. That's what we had in our previous problem, okay? So how much are these? 6 kips. Why are they 6 kips?
One on each side.
There's one on each side, right? Make sense? So this P, in this case, is 6 kips. Okay? So help me out. What are the reactions going to be? 12 kips. So already we now know the reaction on the girder is 12 kips. Let me write those down. me write those down. So. Okay. So with this, what we can do is we can say, all right, let's draw a shear diagram. What's the shear diagram look like? It's going to go up, over, down, over, down, over, down, over, down, over, up, right? That's what our shear diagram is going to look like. Right? And from there, we can draw a moment diagram and go from that, right? I'm not going to draw the moment diagram, but I'll make a point about it. You know what the heck? Let's go ahead and draw it. Because, why not? It's our last hoorah. Okay? So look at this. So each of these are 10 feet. So for the shear diagram, what's that area? That's 120. That's 60. 120. Okay, so am I going too fast on this, or are you all good? That good? Okay. So our moment diagram is going to be like this. It's going to go up, over, down, down. So 0, 120, 180, 120, and then back to 0. So remind me, what was the M max for the beam? What was it, 22.5? And what's our M max for the girder? 180. So again, like a lot more load that it's responsible for. Did I do something wrong?
I think you forgot the 0 section on your moment diagram.
Oh, you're right, I did. You're 100% right. Yeah, so it's supposed to go like that. Ugh, that's bad. You're right. That's what it's supposed to look like. Thank you. But you see what I'm talking about? Like in terms of the magnitude. So those girders, so think in terms of size, they're going to be a lot bigger than the beams, right? Because they're responsible for more. Okay? With me so far? Now, I will say one thing as a rule of thumb. There is no hard and fast rule when you're dealing with girders as to which method you should use. Like, should you use the point load method or should you just treat it like a big old distributed load? If you had a girder that had 80 beams framing into it, you're probably not going to get much of a difference in your answer if you just treat it as one big distributed load. My rule of thumb is if you have any more than 4 beams framing into it, just treat it like a distributed load because it's going to be a lot easier and you're going to end up getting the same answer. So there's no real hard and fast rule on that though. Okay, but I wanted these data points right here because I want to show you what happens with the column. Okay. So let me drag this up here. Okay, so let's consider the column. Which column did we pick? B2? Okay, so treating it with point loads, though, gives you a nice little analogy here at the end. Okay, so here's column B2 right here. Okay, so let's look at the tributary area. So the tributary area for the column is halfway over to the next column, halfway over to the next column, halfway over to the next column, halfway over. So, come on, turn the pan on. So that's what happened. So that's our tributary area for the column. Okay? Now, I want to show you two ways that we can compute the load on the column. What is the tributary area of that column? How do we compute it? It's not a trick question, it's simple. Not 150, but you're close. 1,500, right? Because it's 50 feet, 30 feet. So therefore, the load on the column, I'll call that big P, is that. I think I can do that one in my head. I think that one's what? 30,000 pounds? Or 30 kips, is that right? Now that's one way of looking at it. Okay? Here's another way of looking at it. There's RB is 3 kips, RG is 12 kips. Let's look at this column. How many beams frame into that column? 2. One up top, one below. How many girders frame into that column? 2. One from the left, one from the right. So therefore, you could say uh, 2RB plus 2RG and you can get the same answer. Okay? It's like that static stuff doesn't lie. Okay? So either way works. So, because what we're doing is we're treating the load one-to-one, right? In method 2, all the load that goes onto the beams finds its way to the girders. Okay? So as long as you're accounting for all the load correctly, you'll get the same answer. Okay? And I want to be clear, that 30 kips on that column is only from a single story. Okay? Let me explain what I mean. This is what, a 4-story building that we're in right now? So let me ask you a question. What if this is a 4-story building and we'll say floors equally loaded?
120 kips.
Well, yes, but I want to be, bear with me. I want to be clear on something, okay? So the answer is yes on the ground, but I'm making a point on something else. All right, so what I'm going to do is I'm going to draw sort of the building like this. So okay, so what I've got is I've got this column coming up out of the ground, and I've got floors sticking out of it like that. Now we're talking about column B2, so technically there'd be floors here, here, here as well, and also in and out of the screen. But just for the sake of discussion, I think this image is going to be fine. Okay. Now what I'm saying is that each floor is going to supply 30 kips. Okay, so can somebody tell me how much force is in the column right here? 30 kips in compression. What about right here?
60.
There you go.
90.
There you go. And so the building only, the columns only see 120 kips at the bottom, right? So if you ever, so you can make some, observations about building design right off the bat, and I actually want to talk about this a bit. So if we're looking at columns, where are the columns going to be the biggest? On the bottom floor, right? So really, and this is a little bit of a cartoonish way of drawing it, but columns in buildings kind of look like this. They get smaller as you go up, right? Because they don't have to support as much load, okay? Now, here's another question. If we're talking about gravity load, which is what we're talking about, gravity load, which is in the direction of gravity, which columns are going to be the smallest in the building?
The outside ones?
Not just the out, not the out, well, more specifically. The corner columns. The corner columns are going to be the smallest, right? Why? Because their tributary area is the smallest, right? Okay? The edge columns are going to be twice as big, theoretically, right? Because the edge columns, so think, the corner column, what's the tributary area of this corner column, right? It's just that small little bit up there, right? The tributary area for the edge columns is twice that of the corner columns. And then the interior columns are twice of that, right? So if we're talking about gravity columns, the smallest ones are actually the ones on the outside. Now, in reality, that ends up not always being the case, because the outside columns not only have to withstand gravity acting up and down, but they have to withstand wind going this way. And so it's the outside columns that usually tend to do most of your work on the wind load, which are going to be, let me ask you this. Where are your smallest girders going to be? Not beams, girders. So the girder that we looked at was this one. Can anybody point to a girder that's going to be smaller?
The one to the left? C1D.
I'm talking about the girders, the ones that are going left to right, the one above, C1D1. Yeah. Now, what you were talking about, I think, was the beams. The beams over here on the left, their tributary width is, what's the tributary width of this beam right here? 5 feet, right, because this one's 10 feet, right? Does that make sense? Any questions on that? All right, we're running out of time, so what I'll say is I have a homework assignment where I'm giving you a floor plan, and I'm going to ask you some similar questions about this floor plan. But any questions about the idea? Well, one other thing. On Friday, we have our exam review. So come prepared with questions. And don't forget your course eval if you haven't done it. Homework 9.2, this is the last homework assignment of the semester. I'm not accepting late homework on this one because I'm giving you the solution right as class starts. Okay? Sound good? I'll pull the code up one more time. I'll see you all on Friday.